So thank you for the introduction. I'm Alberto Boaron from University of Geneva. And today I'm speaking about long-distance QKD by presenting you an experiment we performed in Geneva. So at the time of the abstract submission, we had reached a distance of 379 kilometers. But then we improved the system, trying to reach the limits, and we achieved the final distance of 421 kilometers. So I also want to start my talk by showing you the first QKD experiment, where the quantum channel was composed of free space with the distance of just 32 centimeters. And a half, yeah, okay. Makes a huge difference. So then, a lot of progress has been done. So both in fiber optic and in free space QKD. Wanted to mention these two experiments, one between two islands of the Canaries, the other one that we all know now between the satellite and the ground station. And this experiment are a very impressive technological realization, but they are also very demanding in terms of technology and cost. So in Geneva, we are more focusing our research on developing systems based on off-the-shelf components, and but we can also obtain very good performance with this. So since we are talking about long-distance QKD, and this experiment is trying to reach the limits of, or go towards the limits of long-distance QKD, it's interesting to address the question, what does ultimately limit the transmission distance in QKD? And so the answer I want to give could sound a bit surprising, but I will motivate it during this talk. So the limiting factor is the acquisition time. That is, the time a user is ready to wait to obtain a secret key. So our protocol is a simplified version of a BB84 protocol, and we implement it with time-bin encoding and use the decoy state method. So time-bins qubits are composed of two temporal bins, and the weak coherent pulses are either in the first or second time bin for the Z basis. And in the X basis, you have a superposition of these two pulses that have a phase either 0 or pi. So this is for the 4-state BB84. And regarding the decoy state method, the most common way of implementing it is with 3 intensity levels. This is the 2 decoy state method. So the 3 states are usually denoted as signal, decoy, and vacuum. So the first simplification we have done to this protocol is to remove the third state. So we use just one decoy state method, 2 levels in total. And actually, it turns out that this method is slightly better than the 2 decoy one for most experimental settings. So here you have the secret key rate difference between the 2 protocols as a function of the global attenuations. So it's slightly better, and obviously, it's simpler to implement because having only 2 levels instead of 3 is much simpler. So you can learn more about this during the poster session where my colleague Davide Rusca is presenting this paper. So let's come back to the protocol. The second simplification is to remove the 4th state. So we use a 3-state BB84, which was proven to be secure more than 10 years ago. Now, why this is nice? This is closely related to the way we implement this. So we start with a pulsed laser, and the pulses go to an interferometer, an unbalanced interferometer that generates pairs of pulses. And then the states are encoded by an intensity modulator in order to generate these states. On Bob's side, the setup is very simple. The Z measurement is just direct measurements of the arrival time of the photon, while in the X basis we have an interferometer, and we are monitoring just one output of this interferometer. So the measurement in the X basis corresponds to projection, not in the plus state, but instead onto the minus state. So in the end, a BB84 is a protocol with 4 states prepared by Alice and 4 possible detections at Bob, while our protocol has 3 states at Alice and only 3 states at Bob. And we have demonstrated the security of this protocol, and the proof is available since yesterday on the archive. So now, let me show you the elements we implemented to reach long distance. So first thing is to have a very good source, which means a source with a very high repetition rate. Our source is based on a phase-randomized DFB laser with a pulse repetition rate of 2.5 gigahertz and pulse duration of 30 picoseconds. This means that the modulation here performed by the intensity modulator is performed at 5 gigahertz. Having such high speeds makes that the dispersion of the quantum channel becomes an issue. So we have to compensate for the dispersion. And for this purpose, we use compensation fiber made especially for us by Corning, because these fibers are not anymore used in classical communications. Second element is to have, I forgot to mention something important, is the fact that this compensation fiber is part of Alice setup. So it's placed before the final attenuation, and therefore its loss doesn't account in the quantum channel loss. Second point, having very good fibers, we use the Corning ultra-low-loss fibers that most of you should know, because already a few experiments of QKD have been performed with these fibers. These fibers are commercially available, and they have a loss around 0.16 dB per kilometer. However, including fiber loss, including splices and connectors, the effective fiber loss is around 0.17 dB. Third element, very good detectors. So we use superconducting detectors that are manufactured by members of my group. And the main feature is having very low dark counts. We achieve very low dark counts by filtering the blackbody radiation that comes from the fiber which is outside of the cryostat. So this filtering is performed with 2 methods. One is a narrowband filter placed inside the cryostat, and which filters wavelengths around the laser wavelengths. And for longer wavelengths, we use coils of fibers placed also inside the cryostat that filter the longer wavelengths. So with this, we achieve a dark count rate as low as 0.3 counts per second. We have also quite good efficiency, up to 50% at these low dark count rates. And the third element is that we need very good timing jitter, which is 30 picoseconds. And this is a requirement due to our very fast encoding scheme. So putting all this together, we get qubers that can be as low as 0.5%. And the other requirement is to have good stability over time. So the sources of instability are the channel length fluctuations and the interferometer's phase fluctuations. So we compensate these two fluctuations with active feedbacks. Now we come to the results, the main result, which is the secret key rate as a function of the fiber distance. So for the first 4 points, the data was acquired by letting the system run continuously with no interruption. While for the last point, which is 421 kilometers, the detection rate is so low that the stabilization is more challenging to perform. And so we interrupted sometimes the measurement to readjust the alignment. So this point, the 421 kilometer, was obtained with a total acquisition time of 24 hours. However, the data that is really used comes from only 12 hours of measurement, but we calculated the final secret key rate, 0.25 bits per second, using in a fair way, using the 24 hours overall acquisition time. Another thing I would like to stress is the fact that for all points, including the last point, we used finite key analysis. And about the finite key analysis, as the fiber distance increases, we had to reduce the block size. And for the last point, the small block sizes leads to the fact that the finite key analysis reduces the secret key rate by about a factor 1/2. So if we compare these results with previous experiments, the first two experiments, point 1 and 2, we are about 2 orders of magnitude higher. And compared to the only experiment that reached similar distances, around 400 kilometers, we are 4 orders of magnitude, but this experiment is, as you know, an MDI QKD scheme. So we can ask ourselves, how close are we from an ideal system? What can we still improve? So let's consider an ideal system, which is a system based on BB84 encoding. We take the same repetition rate, 2.5 gigahertz. We take perfect detectors, no noise, perfect detection efficiency. And we take the same block size than our experimental points. And so you see, these are the green triangles, that we don't gain more than 1 order of magnitude. Moreover, most of the difference is explained by the difference in detection efficiency. And it's also important to say that our protocol, so this simplified BB84, doesn't lead to significant secret key rate reduction compared to a BB84. So what can we still do compared to this almost ideal system? We could try to improve the repetition rate. So how much can we improve the repetition rate? So let's look at the classical communications. Classical communications use modulation speeds up to 40 gigahertz. And this is really a limit that is very, very hard to beat. And moreover, classical communications has a less restrictive requirement because they need only 3 dB modulation in intensity, for instance, while in QKD we need phase randomized states, and we also need very high extinction in the modulation. So 40 gigahertz really seems a goal that cannot be reached. So let's simulate a system, an ideal system with 40 gigahertz repetition rate. This is what we get. So first, we see that if we place ourselves around 1 hertz of secret key rate, which is more or less secret key rate that is still practical. Going to much lower secret key rates becomes quite unpractical. We see that we are around 600 kilometers. And now, something is missing here. It's the time of acquisition, because this is for an infinite key. And now, if we bound the acquisition time to 1 day, then we obtain the typical cut. And you see that for 1 day, the cut is around 600 kilometers. So I hope that with this, I convinced you that the ultimate limit is the acquisition time, because the acquisition time cannot be increased at will, because it would have to be increased exponentially, which is obviously not possible. So, as a conclusion, I've presented a system that is mainly based on off-the-shelf components. And with this system, we have achieved record-breaking secret key rates of 421 kilometers of optical fiber. Thank you for your attention.
Okay, thanks for the talk. Any questions?
Thanks for the talk. I have one question about how do you synchronize Alice and Bob?
So both Alice and Bob are controlled by an FPGA, and they are linked by, I can show you here. So they are linked by a service channel based on SFP transceivers.
Yes, because you know on each FPGA board they have individual crystal oscillator, and use them as a clock, as a working clock. Because in each FPGA they will have little frequency differences. How do you overcome?
Yeah, but Alice and Bob share a clock.
How do you share the clock?
They share this clock through the service channel. It's a fiber, yes.
Okay, maybe can we talk later?
We can talk.
Okay, thank you.
So basically, you do the experiment in the lab. You don't go to different locations.
Yeah, it's real fiber, but it's not installed fiber. Yeah, it's spooled. You could see here. So here are the fiber spools. So the 421 kilometers fit inside these 4 boxes. This is for the dispersion compensating fiber.
Okay, thank you.
Okay, any other questions? Oh, Jill?
Thank you. Do you have any prognostic how good this would become if it were installed in the field? If it were installed in the field instead, a real life situation, how good do you think you could be?
So first of all, the loss, usually the connection loss are worse, but I guess we wouldn't be much affected by fluctuations because time-beam encoding is very resilient, and I don't think the stabilization would be a big problem. Obviously, it depends on, for instance, if you use fibers that are underground, they are quite stable in temperature. So they could even be better in temperature stability than our fibers in the lab.
Okay, I have a quick question. So I only see your results in the long distance. I didn't see any results in the short distance. So I'm questioning about your detector may saturate in short distance. Say, do you have any results below 50 kilometer fiber?
No, for now we focused on long distance, but already these SNSPDs could have quite high detection rates of more than a megahertz.
Hi, I have one quick question. I was wondering, because your system repetition rate is really high at 2.5 G, some of the modulators probably would go to about 5 G. repetition rate. So I was wondering if you could give us more details on the electronic pulses that you use to modulate these pulses, for example, the pulse width and waveforms and such.
Yeah, so so basically the state is 400 picoseconds long, so each time being is 200 picoseconds, and the electronic pulses have the same duration.
Have the same. Is it like in a square pulse or?
Yeah,
sine?
it's squared, but it's not returned to zero.
It does not return to zero.
No.
Okay. Okay. Thank you.
Okay, so let's thank speaker again.